Alright, so today we're going to be looking at another part of applied mathematics. Our focus today shall be in numerical methods, and we're going to be looking at the very first topic right here. So we're going to be focusing on errors in this video. Alright, let's learn about error analysis. Alright, so error analysis. Alright, so when solving mathematical problems using numerical methods such as iterative techniques or approximations, errors inevitably occur due to the discrete nature of computations. So errors can arise from various sources, including round-off errors, truncation errors, and algorithmic errors. Error analysis helps us to quantify and manage these inaccuracies, ensuring the validity of our results. So there are different types of errors. So there are those that we call round-off errors. So these occur when a fixed number of digits are used to represent exact numbers. For example, we know that 1/6 is actually 0.166666 infinitely. You can actually try that in your calculator and you will actually see that that's what you get when you press in 1/6. So we may decide to round off this value to 0.167, and actually we realize that when we do that, we actually cause what we call a round-off error, because 0.167 is not the same exact value as 0.1666 infinitely, but we've just tried to round it off, so that causes an error. There are also those we call truncation errors. So these occur when an infinite process or a continuous function is approximated by a finite series or algorithm. For example, in binomial theorem, if we use only the first three terms, we've actually caused a truncation error. So if you are familiar with binomial theorem, you may actually understand what I'm talking about. You may choose not to use all the terms because it's actually an infinite process. But you can choose to use the first three terms, the first four terms, or as many as you're actually asked to, depending on the project you're working on. Alright, we also have algorithmic errors, and these occur when there are mistakes or flaws in the design and implementation of algorithm or code. Now this is actually makes more sense to those who are computer programmers. So they are also called logical or programming errors. Unlike numerical errors, which arise due to limitations of numerical methods, algorithmic errors are related to the logic and structure of the code itself. For example, syntax errors in code. So you as a mathematician, if you actually don't focus so much on IT, you don't need to think so much about what algorithmic errors are, but maybe in the future, as your knowledge of computing grows, you actually understand what these are. Alright, so thus in numerical techniques, the magnitude of the error associated with an approximate value may be defined as this. So error is equal to the exact value minus the approximate value. Now, we should note that blunders and mistakes from human mistakes aren't considered to be errors since they can be treated numerically. So just know that. Now, what is the exact value? The exact value refers to the precise, ideal, or theoretical value of a quantity or expression. It represents the value that is calculated without any errors or approximations. So just know that's what we mean by the exact value. Now the approximate value, it is an estimation or a close value of a quantity or expression that is calculated with limited precision or numerical methods. It is a value that is close to the exact value but is not the exact value itself. So remember the example that I gave when I was actually demonstrating the rounding off errors, where I said 0.166 infinitely, we rounded it off to 0.167. So think of 0.1666 infinitely as being the exact value, but then when we rounded off, we got an approximate value, of which that value 0.167 is just close to the exact value. So I think that should actually give you a better understanding of that. Alright, so now there are those notations and symbols we used in error analysis. So now in most cases, so just note this, it's not every time that we actually do this, but in most cases, uppercase capital letters, e.g. X, Y, Z, are used to denote the exact quantities. So in most cases this is true, and then this implies that lowercase letters small x, small y, and small z will be used to denote approximate or estimated quantities. But now this should not be crammed because it can also be in reverse, so it will actually depend on the nature of the question. So if you have a question where small x, small y, and small z are representing the exact quantities, what that means is now the uppercase letters shall be used to denote the approximate values. So just know that. So this should not be crammed, but each one can actually be reversed. So therefore, if capital X denoted the exact value, then small x will denote the approximate value. Now also know that if small x denotes the exact value, then capital X will denote the approximate value. So that is very, very important. So we should not cram that. So this should be understood. So they can actually be used in reverse. So also, if small x is an approximation of capital X, the error in small x can be denoted by this. As you can see, we have delta x, we have sigma x, and then we have ex, and is got by subtracting the approximate value from the exact value. So now we're looking at a case where small x is the approximation and capital X is the exact quantity. What that means is that error in x shall be equal to the exact value, which is capital X, minus the small x. Or we can write it as this. We can write as sigma x is equal to capital X of minus small x. Or we can also write it as ex is equal to capital X minus small x. So now this should not be crammed, but we should actually just understand it. So I can choose to use any of these ways to represent the error in x, and it is all okay. So it will depend on the question. So in some cases you see delta x, other times you see sigma x, other times you see ex, depending on which one that I want to use. But just know that each one of these is correct for representing the error in x. So let's look at some terms used in errors. The first term we shall look at is absolute error. So absolute error refers to the difference between the true value and the approximate value. Now, in general, the maximum absolute error when a number has been rounded off to n decimal places is given by 0.5 times 10 to the power negative n. So this is very, very important for us to remember. So what that means is, for example, if a number has been rounded off to 3 decimal places and x is equal to 0.072, then it actually means that we actually look at these 3 values here. So we can actually say that there are 3 values after a decimal place. That means we have 0.5 times 10 to the power negative 3. So we consider the number of decimal places. So there are 3 decimal places. So that means we'll have 0.5 times 10 to the power negative 3, of which the answer shall be 0.0005. So that's how we find the maximum absolute error in this case. That's the maximum absolute error in x. Now, where x is the maximum absolute error in x, just as we've said. Now, let's look at another term, relative error. So this is the ratio of the absolute error to the true or exact value. So we can have relative error being equal to absolute error over exact value, or, so there are 2 ways we can actually go with this. So it can also be absolute error over the working value. So this is just another way of writing it. Now, we're going to look at 2 different ways of actually working with error numbers. Now, there are 2 different ways. We're going to have that which is called interval arithmetic, which is binary operations of rounding errors using interval arithmetic. But there's also another section that we shall look at in the second video called error propagation. So both of these methods can be interchanged depending on the context of the question. But we're going to begin with interval arithmetic. Now, in interval arithmetic, this involves getting the error in an expression by first calculating the maximum value, minimum value, and approximate or working value. After getting these, the error in the given expression can be got from absolute error is equal to maximum value minus minimum value over 2. Interval or range shall be equal to, so we shall get the minimum value, comma, to the maximum value. That's how we find the interval or range. So just know that the words interval and range are interchanged depending on the question, but they actually mean the same thing. Then the limits can be got from working value plus or minus absolute error. Upper limit shall be equal to maximum value. Upper limit represents the maximum value, so that is working value plus the absolute error. The lower limit shall be the minimum value, of which that is working value minus absolute error. So just know that there is also another way we can write this. So I may say upper bound instead of upper limit. So there may be a context of a question where I say upper bound. That means the exact same thing as upper limit. Then lower bound shall also mean the same thing as lower limit. So make sure you know that these words can be interchanged. Relative error shall be equal to absolute error over the working value or the approximate value. And then percentage error shall be equal to relative error times 100%. Alright, now we're going to look at maximum and minimum value in addition. Now if I'm going to sum up two different values and I want to find the maximum value that can exist among them. Alright, so we're going to suppose that small x is equal to 3.22 and y is equal to 2.2 have been rounded off to the given number of decimal places. So this implies that the maximum absolute error in x shall be got from 0.5 times 10 to the power negative 2. So observe that x is to 2 decimal places. That's why we have 10 to the power negative 2. So we shall have 0.005. And then the error in y shall be found from 0.5 times 10 to the power negative 1 because we actually have one decimal place. So we shall have it as 0.05. Now there are four possible alternatives for adding the two values x and y, and these are as follows. Now we shall have x minimum plus y minimum. Let's look at what happens in this case. Now to get x minimum, that definitely means we shall actually have 3.22 minus that error in x to get the minimum, and then to get the minimum in y it shall also be 2.22 minus the error in y, and the answer shall be 3.215 plus 2.15, which shall give us 5.365. Now let's look at another alternative. We can have x minimum plus y max. To get x min we shall also have 3.22 minus 0.005, but now to get y max we shall not subtract off this, but we shall now add its error. So we shall add 0.05, of which we shall get 3.215 plus 2.25, which shall give me 5.465. Now there is also another alternative where we can have x max plus y min. That means that on x we shall actually add the 0.005, so we shall have 3.22 plus 0.005, and then where we have y min we shall have 2.2 minus 0.05. Remember, at the minimum we subtract and at the maximum we add. So we shall have 3.225 plus 2.15, which shall give me 5.375. Now another alternative can be x max plus y max, which shall be 3.22 plus 0.005 plus this shall give me 2.2 plus 0.05. So I'll have 3.225 plus 2.25, which shall give me 5.475. Now from our observations from the above alternatives, we can see that 5.365 is the smallest value, which implies that x min plus y min gives the minimum value for addition. So the smallest value possible for addition of x and y comes from x min plus y min. Then we can also see that 5.475 is the largest, and this implies that x max plus y max gives the maximum value for addition. So what this simply means is that x plus y min, that the minimum value of this addition shall come from x min plus y min, and then the highest or greatest value of the addition, which is the x plus y max, shall come from x max plus y max. So these shall be what we shall use. So we're going to put these in brackets for our remembrance. So we're going to put this in a yellow box for our remembrance. Alright, so let's look at the case of subtraction, maximum and minimum value in subtraction. Now suppose x is 3.22 and y is 2.2 have been rounded off to this given number of decimal places. So we're going to have the same exact thing, and now we're going to look at the case where we actually have subtraction. Now remember, there are also going to be four possible alternatives when you're actually subtracting the two values x and y. Let's look at x min minus y min. We shall have 3.22 minus 0.005 minus 2.2 minus 0.05. This shall give me 3.215 minus 2.15. So I'll have 1.065. Let's look at another alternative where we have x min minus y max. So now in this side I'll subtract and in this side I'll add. So what will I get? I'll get 0.965. Now what if I have x max minus y min? I'm going to have 3.225 minus 2.15, which shall give me 1.075. And then let's look at the case where we have x max minus y max. This shall give me 3.225 minus 2.25, which shall give me 0.975. Now from the above alternatives, you can see that 0.965 is the smallest value, and this implies that x min minus y max gives the minimum value for subtraction, or the smallest value for subtraction, and then 1.075 is the largest, implying that x max minus y min gives the maximum value for subtraction. Now this means that the minimum value of subtraction x minus y will come from x min minus y max, and then the maximum value of subtraction, which is x minus y max, shall come from x max minus y min, and these shall be put in a yellow box for our remembrance. Let's look at the next case where we have maximum and minimum value for multiplication in multiplication. Alright, so now we have the same situation here, but let's look at the different alternatives. So the first alternative can be x min times y min, which shall give me 3.215 x min times y min, which shall give me 3.215 times 2.15, which shall be 6.91225. Then we also have the case of x min times y max, which shall give me 3.215 times 2.25, which shall give me 7.23375. Then we also can look at x max times y min, which shall give me 6.93375. Then we have x max times y max, which shall give me 7.25625. Alright, so from the above alternatives, 6.91225 is the smallest, implying that x min times y min gives the minimum value for multiplication, and then 7.25625 is the largest, implying that x max times y max gives the maximum value for multiplication. Now in summary, we can see that the minimum value for multiplication of x and y comes from x min times y min, and then the maximum value in the product of x and y comes from x max times y max. We're going to put them in a yellow box for our remembrance. Alright, now let's look at another case where we have maximum and minimum value in positive. Alright, so let's look at another case where we have maximum and minimum value in positive quotients. So observe, I've said quotients that are positive. Now when it comes to division, we're going to have three different cases, and that is when both numerator and denominator are positive. We're going to have another case where the numerator alone is negative and the denominator is positive. Then we're also going to have another case where the numerator is positive and the denominator is negative. So this is a case where we actually have to pay very much careful attention. So this implies that this is what we'll have. So the four possible alternatives in positive quotients are x min over y min, which shall be the first case, with this shall give me 1.49535. Then we have x min over y max, which shall give me 1.42889. Then we also have x max over y min, which shall give me 1.5. We can also look at the last alternative, which shall be x max over y max, which shall be 1.43333. So from the above alternatives, you can see that 1.5 is the largest, implying that x max over y min gives the maximum value for positive quotients. Then we can see that 1.42889 is the smallest, implying that x min over y max gives the minimum value for positive quotients. Now in summary, we can see that to get the minimum value in these quotients that are positive, we shall have x min over y max, then the maximum value shall come from x max over y min. Put these in a yellow box for remembrance. Alright, so let's look at the case where we have maximum and minimum value in quotients with a negative numerator. So now we're going to suppose that x is negative 3.22 and y is 2.2. Let's see if the case shall actually be different. Now we can clearly see that x min over y min, which is the first alternative, shall be this. So we're going to have negative 3.225 over 2.15, which shall give me negative 1.5. So observe that in this case, we're going to have a negative here. So this means that something will actually be different. Now x min over y max shall give me negative 3.225 over 2.25, which shall give me negative 1.43333. Now we're going to have x max over y min, which shall also give me negative 1.49535. Then lastly, we're going to have negative 1.42889 for x max over y, max. Now from these alternatives we can now see that negative 1.42889 is the largest, implying that x max over y max gives the maximum value for quotients with a negative numerator. Then we can say that negative 1.5 is the smallest, implying that x mean over y mean gives the minimum value for quotients with a negative numerator. So in summary, we can set in this case negative x over y mean shall be equal to x mean over y mean. Then we can also see that the minimum value for quotients, the maximum value for the quotients shall come from x max over y max. For this case here, we have a negative numerator. So we have this in a yellow box for remembrance. Alright, let's look at the last case where we look for maximum and minimum value in the negative denominator. So we're going to suppose that x is 3.22 and y is negative 2.2 have been rounded off to the given number of decimal places. So now these are the errors in x and y. Then the four possible alternatives shall be this. So we're going to have 3.22 minus 0.005 over negative 2.2 minus 0.05. So we're going to have the answer as negative 1.42889. Now for x min over y max we shall have negative 1.49535, and then x max over y min shall give me negative 1.43333, and then x max over y max shall give me negative 1.5. So from these alternatives, you can see that negative 1.42889 is the largest, implying that x min over y min gives the maximum value for quotients with a negative denominator. Then you can also say that negative 1.5 is the smallest, implying that x max over y max shall give me the minimum value for quotients with a negative denominator. So in summary, we shall have it this way. So for quotients with a negative denominator, the minimum value shall come from x max over y max. Then also for the quotients with a negative denominator, the maximum value shall come from x min over y min. So we're going to have this in a yellow box for remembrance. So now in summary, these are the formulas that we actually derived. I encourage you to memorize them for it to make your work easier in this topic. So these we're going to use in approaching the different questions for this part of interval arithmetic. Alright, so let's look at a question from UNEB 2005, and this was question number 8. So it was saying, given that the numbers a is equal to 23.037 and b is equal to 8.4658, measured to the nearest number of decimal places indicated. Part 1, state the maximum possible errors in a and b. And then in part 2, determine the absolute error in a over b. And then in part 3, we're being told to find the limits within which a over b lies correct for decimal places. So let's look at how to solve this. Now let's solve for a first. Let's look at a alone, and we're going to first find the error in a. So error in a, EA, we're going to use EA this time. Remember, you can have it as delta A or sigma A, it doesn't matter. We're going to have EA being equal to 0.5 times 10 to the power negative 3, because we can actually set it is to 3 decimal places, of which we shall have error in A shall be 0.0005. Then solving for small b, error in b shall be 0.5 times 10 to the power negative 4, because it is actually to 4 decimal places. So the error in b shall be 0.00005. So therefore, the maximum possible error in a shall be 0.005, and the maximum possible error in b shall be 0.00005. Now in part 2, we're being told to determine the absolute error in a over b. Alright, so for part 2, we're going to first get the a over b max. So we're going to look at that case. So remember that when we are looking for the maximum value of division of both positive quotients, the reason I know that they're both positive quotients is we can actually look here that a is 23.037, which is positive, and b is also positive. So we're dealing with positive quotients. So now when we find the maximum in positive quotients, we're going to remember and look back to the formula. So remember that when we're looking for the maximum value, we shall have it as x max over y min. Now in this case where we have a and b, that means we shall have a max over b min. So what that means is we shall have a max over b min, which shall be 23.037 plus 0.005, and then 8.4658 minus 0.0005, of which I'll have 2.721259. I encourage you in such numbers to always at least put to 6 decimal places. It doesn't mean that it's what is required. Unless in the question they specify for you how many decimal places to use, but just do it at 6 minimum so that we actually have more precise answers. Let's look at the A over B mean. If I go back to the formulas, you can actually see that I'll have the minimum at the top and the maximum below. So I shall have A mean over B max for that case. So this is what we shall have, of which I'll have 2.721109 in that case. So remember that whenever we're looking at the minimum side, we subtract, and then when we're looking at the maximum side, we add to the error to that number. So now the absolute error shall be the maximum value minus the minimum value over 2. So the maximum value in the quotient A over B shall be this, and then the minimum value in the quotient, positive quotient A over B, shall be that. So put them together, divide by 2, and I'll have the answer as 0.000075, and that is the answer. So in part 3, we're being told to find the limits within which A over B lies correct to 4 decimal places. Alright, so now for part 3, we shall already see that we already know the upper limit. So the upper limit shall be the maximum value, which is gotten from here, but we shall round this off to 4 decimal places as required. Then the lower limit shall be this rounded off to 4 decimal places. So the upper limit shall be 2.7213 and the lower limit shall be 2.7211, and those are the answers. So the next question is a question from UNEB 1998, and this was question 9A. So being told that given that the values of x is equal to 4, y is equal to 6, and z is equal to 8 each have been approximated to the nearest integer, find the maximum and minimum values of 1. Y over x, 2. Z minus x over y, and part 3. X plus y bracket times z. Alright, so let's solve this. So we're going to first solve for x. So we're going to first find the errors in each one of them. Now you can actually see that each one of them doesn't have any decimal place. So that means that now we shall actually have a 0. So it's 0.5 times 10 to the power 0. So we shall have the error in x as 0.5. Now we shall also look for the lower bound in x. Now that shall actually save us time so that we actually do things faster. So x mean shall be 4 minus 0.5, which shall be 3.5. And then the upper bound, which is x max, shall be 4 plus 0.5, which is 4.5. So I'm going to be doing this in this case to actually save time, so we don't have to calculate them every time. Then when we solve for y, we shall set the error in y, which shall be 0.5 times 10 to the power 0 also, because there are also no decimal places there. So we shall have the error in y as 0.5, and then the lower bound in y, which is y min, shall be 6 minus 0.5, which is 5.5, and then the upper bound, which is the y max, shall be 6 plus 0.5, which is 6.5. And then for z, we're going to have error in z as 0.5 times 10 to the power 0, also because it has no decimal places. So we shall have 0.5. Its lower bound, which is z min, shall be 8 minus 0.5, which is 7.5, and then its upper bound, z max, shall be 8 plus 0.5, which is 8.5. So now that we know all these, we shall actually do things faster. So in the very first one, we've been told to find y over x. So we're going to first find the minimum, and then we shall find the maximum of y over x. So now y min, as you remember from the formulas, shall now be y min over x max. We can actually confirm that. We actually look here, so we shall have the mean over the max for that case. Now the reason we're able to do that is we've already confirmed that both the one at the top and both the one at the bottom are all positive quotients. That means y is positive and x is positive. So that means we don't need to look at these, so we shall just focus on this. So that's what we have. And then we shall have 5.5 over 4.5, which shall be 1.22222. Then y over x max shall be x max over y over x min. Let's look at that. It comes from here. So have the maximum over the minimum. And then we shall have it as 6.5 over 3.5, which shall be 1.85714. Alright, so now we have the maximum and the minimum. Alright, and then since this is what the question wanted, the question was just telling us to only find the maximum and minimum values. So these shall be the two different answers. Alright, so in the next part, we're being told to find that for z minus x over y. Now, for us to confirm that these are actually not negative quotients, we actually have to first confirm something. Now let's look at this. So when you say z minus x, be very, very careful. Now let's look at the value of z. Z is 8 and then x is 4. What is 8 minus 4? 8 minus 4 is positive 4 and y is actually positive 6. That means we shall end up having 4 over 6. So that means we're actually dealing with positive quotients. So that means we can actually use the rule of positive quotients for that case. So when we're finding z minus x over y mean, we shall look at the positive quotients again. So that means we shall just focus on the positives here. So now let's actually first divide this. So in find the minimum, we shall have x mean over y max. So it shall have minimum at the top and then maximum at the bottom. So that means we shall have z minus x mean over y max. Now inside here there's also a subtraction. Now we need to look for how to find the minimum value of a subtraction. Now let's look for that. Now when we look here, we can actually see that when we are looking for the minimum, we'll have x mean, which is this first value minimum, minus this value maximum. So that means in this case we shall have z mean minus x max over y max in this case, and this is how we actually break it down. Then we can now put in the values. So z mean is 7.5 minus x max, which is 4.5 over 6.5, and the answer shall be 0.46154. Then we'll look at the maximum part of it. Let's look at it. I'll have a max at the top and the minimum at the bottom. So I'll have z minus x max over y mean. Now we have a subtraction here. How do we get the maximum value of a subtraction? Let's look at it. And then this is what we have. We'll have x max minus y mean. So that means in this case we'll have it as z max minus x mean over y mean. Now the maximum value of z is 8.5, x mean is 3.5, and y mean is 5.5. So I'll have 0.90909 as the maximum and minimum values. Let's look to part 3. So in part 3 we're being asked x plus y times z. So this is product. Alright, so let's look at the product side. So now we're going to first find the minimum of this. Let's look for where we have product of this times that. So when we're finding the minimum, in product we'll have x mean times y mean. So that means we're going to have the minimum, we're going to have it as x plus y mean times z mean. Now let's look at the minimum value of addition. Now when I look at that, I'll have x mean plus y mean. So that means that can further be broken down to be like that. Then I'll have 3.5 plus 5.5 because I know that this is x mean and then this is y mean times 7.5, of which the answer shall be 9.0 times 7.5, which is 67.5, and that is the minimum value. Let's look at the maximum value here. We know that this shall be broken up into, let's look at the maximum value where we involve product. We shall have it as x max times y max. That means here I'll have x plus y max times z max. Now when we look at the addition, the maximum in addition, I'll have x max plus y max, so it's max max. So that means I'll have it as x max plus y max times z max. So I have 4.5 plus 6.5 times 8.5, which shall be 93.5, and this is the answer. So this is actually how we work out this question. The next question is a question from UNEB 2017, and this was question number 6. So being told that given that the values y is equal to 1 over x plus x and x is equal to 2.4 correct to one decimal place, find the limits within which y lies. So how do we solve this? So first of all, we're going to first solve for x. We know that x is to one decimal place, so error in x shall be 0.05. Then let's look at the maximum value of y first. Remember, we're finding limits, so that means we just need the maximum value of y and the minimum value of y. So the maximum value of y, which is y max, shall be the same as finding the maximum value of what we actually have inside here. And as you can see, we're actually dealing with addition. Now when we look at this, we can actually see that when we're actually finding the maximum value, what usually happens is we'll look at this. So we'll have the maximum here and the maximum here. So now what that would actually mean is I'll actually have x max, and then I'll actually have to find the maximum of this quotient here, which is 1 over x. But when we look at finding the maximum here, since this is actually a quotient, I'll actually now also look to what we actually have right here. So we look at the maximum value here. So I'll now also look at this over that. But because we have a 1 here, we should just consider that as a constant. And then now down here, we should actually have to find the minimum of that value. So that's why in this case, we'll have it as 1 over x min plus x max in that case. So that means I'll have 1 over 2.4 minus 0.05 plus 2.4 plus 0.05, which shall give me 2.9 to 1 decimal place. Now that is because we've been told to do that to 1 decimal place. Alright, so now when I look at the minimum value of y, I'll actually see that this is what I'll also have. Now when we look at minimum value in addition, we also can see that we'll have x min plus y min. So that means we will have this x as min. But now here, because this is actually also 1 over x, which is a positive quotient, I'll also look at the min where we actually have quotients. So when I look at that, I'll actually see that I have the minimum at the top and the maximum at the bottom. So that means that now, because 1 is actually a constant, I'll actually consider maximum of x in this quotient. So that's 1 over x max plus x min, which shall give me 2.8 to 1 decimal place. Now that I know the maximum value and I know the minimum value, now it's easy to find the limit. So the upper limit is 2.9 because that's what I get from the maximum, and then the lower limit is 2.8, and these are the answers they wanted. Alright, so moving on, we're going to move to another question, and this was a question from UNEB 2010, and this was question 14b. So I've been told that if n1 is equal to 2.765, n2 is 0.72, determine the range within which the exact values of n1 times n2 times n1 minus n2 lie. So we have n2 minus n1 over n1 times n2 in the second case. So we're going to find where these are expected to lie. We're going to find where the range, where these are expected to lie, and then we're going to give our answers 3 decimal places. So that's what the question says. So now what we're going to do is we're going to first solve for n1. We're going to save time. We're going to find n1 min and n1 max also, and then n2 min and n2 max. So now the error in n1 shall be this, because it's to 3 decimal places. So it's 0.005, and then n1 min shall be 2.765 minus 0.0005, which shall give me 2.7645, and then n1 max shall be 2.765 plus 0.0005, which shall be 2.7655. Then when we solve for n2, I'll find that the error in n2 shall be 0.005. Now you've actually observed that I've actually chosen to use delta in this case. Remember, it's optional. You can use n. I could have said en2, that would also have been fine, but this is what I've chosen to use, so it's still fine. So now we can actually say that the lower bound or the lower limit of n2 min shall be 0.715, and then the lower bound of n2, which is n2 max, shall be 0.725. I mean, that's the upper bound in this case. So now that we know those, we can now actually start solving these. Now I want you to first make sure to note something so that we actually don't make any error as we calculate. First thing you have to ask yourself is when I actually look at this, when I actually get the value of n1 minus n2, you can actually see that I have 2.765 minus 0.72, and that should actually be a positive. So that actually means that this will actually be a normal one to solve. Now the one I want you to focus on so much is these that actually have quotients, so that you actually find out if we're actually dealing with a quotient with either a negative numerator or a negative denominator, because there the cases are actually different. So when I look at n2 minus n1, it shall give me 0.72 minus 2.765, and that shall actually be a negative. So that actually means that I have a negative at the top. So I have a negative, it's, for example, like having negative x over y. So that means this is the case where we actually have a negative numerator in this quotient. So that actually means that we're not going to use the normal ones. We're going to consider those that actually have a negative numerator at the top. So that's actually the unique thing about this number, because if you don't observe that, you'll actually have a wrong answer. Alright, so now let's look at the first part. Now here we're now looking for the minimum. So we're going to first find the minimum, then we should actually find the maximum. Now this is actually dealing with products, and we're looking for the minimum part. Let's actually look for that. So in products, and we find the minimum, it's minimum times minimum. So in this case, because even if there are 3, so it will be minimum on all sides. So I'll have it this way. So I'll actually have the minimum of the product of these two, and then the minimum of what we actually have in these brackets. So these two categories multiplying themselves. Now we also find the minimum here, and then this shall also give me the minimum for these two. Now in this case here, for this side here, we're looking at n1 minus n2 minimum, and that shall actually bring in the subtraction side of it, which shall give me x mean minus y mean max. So it will be mean minus max. So that's why I'll have n1 mean minus n2 max on this side. Now I can substitute in the values, and then when I do, and then I actually calculate, I'll have this. So the answer shall be 4.0313 decimal places. Remember, this was asked for in the question, that these are the decimal places that we should actually work with. So this is the minimum. Now let's look at the maximum of it. So now I'll also have it this way. So when I look at this and multiplying, let's consider these together and then these together. I shall actually see that I'll have max, because that's what I actually get from right here. And then now that means I actually need the maximum value of this subtraction here, which shall give me max minus mean, as you can see right here. So that's why this shall be broken up into n1 max minus n2 mean, and then this shall be max. So now when I substitute in the values, I'll have 4.11123 decimal places. So now when we state the range shall be the minimum value, which is 4.031, comma, and then the maximum value, and that is the answer for the range or interval. Then we move into part 2. We're now going to be dealing with this. Now we're dealing with n2 minus n1 over negative 1 over n1 over n2. So now find the minimum. So remember, we had actually confirmed that at the top we actually have a negative. So that actually means we are looking at another case. So that means is we're looking at this case here, we actually have a negative numerator. So now find the minimum, we actually have a minimum at the top and the minimum at the bottom, or at the denominator. So that means that this shall actually be n2 minus n1 mean over n1 n2 mean. Let's look at the top. So we're finding the minimum of the subtraction, and then at the top we're finding the product of the product, and then we're finding the minimum of this product. So at the top we'll have, so we're going to look at this. So I'll have at the top, I'll have mean minus max, and then down below for the product I'll have x, I will have mean times mean. So this shall be n2 mean minus n1 max over n1 mean n2 mean. So when I substitute in the values, I'll have negative 1.03723 decimal places. Alright, so in dealing with the maximum side of it, let's look at where we actually find the maximum, where at the top we actually have a negative. So when we're finding it, so when we're dealing with the negative numerator, at the top I'll have the maximum over the maximum at the bottom. So now this shall also be n2 max minus n1 mean over n max times n2 max. So this shall give me that the answer shall be negative 1.0173 decimal places. So now the range shall be, I'll look for the minimum value and the maximum value. Now the smaller of these values shall be negative 1.037, which is what we get from the minimum, and then the maximum value, which is this, is negative 1.017, and this is the answer they wanted. Alright, so the next question, we're being told that given that r is equal to 1.50, t is equal to 13.3, and x is equal to 9.200, all rounded off to the given decimal places, find the minimum value of x squared over r minus t, correct for decimal places. Now in such cases, you also have to be very, very careful whenever you see a quotient, because now we can actually see that r minus t is what we actually have at the bottom. So now we can see that r, which is 1.5, minus t, which is 13.3, shall actually be a negative. So what that means is this is a quotient with a negative denominator. So that's actually very, very important to note. So now let's solve for r. So error in r shall be 0.005, and then the error r max shall be 1.505, r mean shall be 1.495. Now let's solve for t. the error in t, remember t is to 1 decimal place, so that actually means we'll have 0.05 as the error in t, of which t max shall be 13.35 and t min shall be 13.25. Now let's deal with x. Now solving for x, error in x shall be 0.005 because we actually have 3 decimal places, so we actually have 3 zeros right there. So now I'll have x max as 9.2005 and then x min shall be 9.1995. Alright, so now when we find the minimum value of x squared over r minus t, remember that right now we're dealing with a negative denominator, a quotient with a negative denominator. So that means that we'll actually look here. Let's look at where we actually have a negative denominator. So this is what we should actually look at. So in finding the minimum, we're actually going to have x max over y max. So it's maximum over maximum. So we have the maximum over the maximum. Now again, here we're actually dealing with product. So that means it's x times x. That actually means we're going to look at the maximum in product, and then we're going to look at subtraction where we actually have maximum. So now when we're actually dealing with maximum in product, we shall have max times max, and then when we're dealing with subtraction in maximum, we'll have max minus min. So that means in this case we'll have x squared max over r max minus t min, of which remember that x max times x max is just the same as actually just squaring the answer of maximum. So now we just have 9.2005 squared over 1.505 minus 13.25. So I'll have negative 7.207324 decimal places. So the question only asked me to find the minimum value of x squared over r minus t. So this is our final answer. Alright, so the next question is the question from last year as of the recording of this video. I'm in the year 2024. So this is a question from last year 2023. So we're being told that the number x is equal to 6.45, y is equal to 0.00215, and z is equal to 2.7 are all rounded off to the given number of decimal places. Determine the interval in which w is equal to x plus z cubed over root of y lies. Now in this case we can actually see that it's a quotient here, but we actually don't have to worry about negatives because at the top we're actually just simply adding. So now we're going to just deal with positive quotients in this case. Right, but to make it easier, we're going to first solve for x. So x, remember, is 6.45, and we can actually say that it has 2 decimal places. So that means the error in x is 0.005, and then the x max shall be 6.455, x min shall be 6.445. Now let's solve for y. Error in y shall be 0.00005, and that's because we actually have 5 decimal places. So now y max shall be that, and then y min shall be that value. Let's solve for z. Z shall be, the error in z shall be 0.05, and then we're going to have the z max as 2.75, and then z min shall be 2.65. And all this is true because z is just simply to 1 decimal place. Alright, so now next we're going to find the minimum value of w. Now this is what we're dealing with, so find the minimum value right here. Now when we look at positive quotients and we're finding the minimum, we're going to have a minimum at the top and a maximum at the bottom. So that means this shall be this. So this is what I'll have. Now when I look at this value right here, let's look at the minimum in addition. The minimum in addition shall be x min plus y min. So that means this is what I'll basically have. Now let's break this down further. Remember now here we're actually dealing with products. Z min, when you're actually dealing with products, it means I have min times min. So that means I actually don't have to worry. I can actually just direct in substitute the products. Then also here, where we actually have y max, it's basically like y to the power half. So that's basically also like talking about products. But when you have such cases, you can actually just plug in the values directly. So this is what I'll have, and then when I actually add this together and then I divide, I'll have 539.714467. Now when I find the maximum value of w, so now when we're doing the maximum of positive quotients, I'll have it right here. I'll have max over min. So this is basically what I'll have. And then when I break down this further, in addition, I have x max plus z max cubed. So now I can just plug in the values, and this is what I'll get: 588.413651. So therefore the interval or the range shall be 539.714467, which is actually the lower value, the minimum value, and then 588.413651, which is the maximum value, and that is the answer they wanted. Right, so the next question is a question saying, given that n is equal to 12.4 over 4.20 minus 10.80 over 6.124, write the possible error in each of the values given, and then next estimate the range of values within which n lies, hence determine the absolute error in n, and also find the percentage error and relative error in n. So this is actually a deep question. It has a lot that it actually requires, but it's actually an easy one. Alright, so let's first solve for 12.4. So now error in 12.4 is 0.5 times 10 to the power negative 1, of which I have it as 0.05. So now the lower bound, which is 12.4, mean shall be 12.4 minus 0.05, which shall be 12.35. Then the upper bound, which is 12.4 max, shall be 12.4 plus 0.05, which shall be 12.45. Let's look at 4.20. This is what I have. It's two decimal places, so that is the error in 4.20. So now 4.20 mean shall be 4.195, and then 4.20 max shall be 4.205. So let's move on to the next value, 10.80, of which the error in it is 0.005. The lower bound shall be 10.795, and then the upper bound shall be 10.805. Let's look at 6.124. It's to 3 decimal places, so the error in it is 0.0005. So its lower bound is 6.1235, and its upper bound is 6.1245. Alright, so that's what we actually found. So part A had only asked for the possible errors in each of the values given. So the answers that we actually need are this 0.05, this 0.005, this 0.005 here, and then also this 0.005. So this is where the marks shall be given. Now I'd actually found the lower bounds and upper bounds of each one of them just to actually make my life easier as I actually solve the different numbers and mean the different parts that are actually upcoming. But that's what we actually wanted in part 1. So the next part had actually asked us find and estimate the range of values within which n lies. So that means I actually first have to find n max and then n mean in that case, and then I'll actually find the rest of it. Alright, so now to find n max, this is what I'll actually be dealing with. So remember I have 12.4 over 4.0 minus this, so actually looking at subtraction. So when we're finding the maximum in subtraction, I'll have the maximum minus the minimum, and that's what actually I'm doing right here. Now when I actually look at this, so now this is actually the quotients. So now when I'm looking at the, remember these are positive quotients, when I find the maximum I'll see what I'll get, and this is the minimum. So in quotients, when finding the minimum I look at mean over max, and then when finding the maximum I look at max over mean. So now just do it as it's needed. So I have 12.4 max over 4.20 mean minus 10.80 mean over 6.124 max. So these are the answers I'll get. So when I plug this in, I'll have it this way, and then I'll have the answers 1.205226. Let's look for n mean. Now when we're dealing with the minimum, when we're subtracting, this shall be minimum and then this shall be maximum. And then when I go into detail, I'll actually find that here I'll actually have a minimum at the top and a maximum below, and then here I'll also have a maximum at the top and a minimum below. So this is what I have. So when I subtract this, I have 1.172464. Alright, so therefore the range is, we're going to look at the minimum value. The maximum minimum value is this value here, 1.172464, comma 1.205226. Now we're told to also find the absolute error in n. So the absolute error, remember the formula is maximum value minus minimum value over 2. So I know my maximum and minimum values, plug them in, and then I'll have the answers 0.016381. Then also told to find the relative error in n. So relative error is absolute error over exact value. So now first of all, it means we need to know the exact value. The exact value means we're going to use the values as they were given in the question and first find that answer. So this is what I actually get from the exact value. So I have 1.18882. So this is the exact value. And then I'm going to have the absolute error dividing that exact value. So this is what I have, and the relative error shall be 0.013779. Alright, so now that I know that, I can now find the percentage error in n. So the percentage error is got from relative error times 100%. So this shall be 1.3779%, and this is the answer they wanted. Alright, so moving on to the next question. So we're being told that the sides of a rectangle are measured as 5.24 and 6.38 to the nearest meter. So being told to calculate the minimum value of the perimeter, calculate the maximum value of the area, and then part C, calculate the minimum value of the area. Hence, determine the absolute error. Alright, so first of all, we're going to let the length L shall be 6.38 meters. So we're going to let that to be the length. Now, the reason we know that L is the length of a rectangle is because in a rectangle generally, the length is the longer side, and definitely 6.38 is the bigger value compared to the 5.24. So 5.24 shall actually be the width of the rectangle. Then we're going to let the width W be 5.24 meters. So now we're going to first look at L. Let's deal with L. So the error in L shall be 0.5 times 10 to the power negative 2, of which I have 0.005. Now the upper bound L max shall be 6.385, L min shall be 6.375. So when I look at the width, the error in width shall be 0.005. The upper bound W max shall be 5.245, then W min shall be 5.235. So being told to calculate the minimum value of the perimeter. So that means we're going to first look at the perimeter. Now remember, perimeter is given as 2 times length plus width. So P min shall be the minimum of that. Now let's look at addition. So now looking at addition and we're finding the minimum, remember we shall have L min plus W min. So we ignore the 2 because the 2 is just a constant. So now I'm going to put in the values, and I'll have 2 times 11.61, which is 23.22 meters. That is the minimum value of the perimeter, and that's what they wanted. Now for part B, we're being told to find the maximum value of the area. Now remember that area is length times width. Then when we're dealing with product and we're finding the maximum, L times W, we shall have L max times W max, which shall be 6.385 times 5.245, of which I have 33.489325 meters squared. Then in part C, we're being told to catch the minimum value of the area and hence determine the absolute error. So for part C, minimum area shall be gotten from this. So remember, when we find a minimum and we're dealing with product, we'll have L min times W min, of which I'll have it this way. So the answer shall be 33.373125 meters squared. So the absolute error in area shall be got from this formula. So I'm going to put the maximum value minus the minimum value of the area over 2, of which I'll have 0.0581, and that is the answer. So therefore the absolute error in area is 0.0581. The next question is a question from UNEB 1999, and this was question 9A. So being told that the area A of a parallelogram formed by vectors A and B given by A times B sine theta, where theta is the angle between the vectors. Find the percentage error made in the area if A and B are measured with an error of 0.05 and theta has been measured with an error of 0.5. Given that A is 2.5 and B is 3.4 centimeters and theta is 30 degrees. So now let's work this out. So we're going to first look at the error in A. So we shall see that we have 0.5 times 10 to the power negative 1, because we actually have one decimal place, of which I have 0.05. Then the upper limit shall be 2.5 plus 0.05. So I have 2.55 as A max. Then A min shall be 2.45. When I look at B, I can set b is to 1 decimal place also, so now the error shall also be 0.05. So the upper bound or b max shall be 3.45 and the lower bound or b min shall be 3.35. Now look at the error in theta also. Remember that we've been told that the error in theta is 0.5. And how do we know that? We were also told right here. So we're told that it is 0.5, or we can actually just look at it here that there is actually no decimal place. So that means we're dealing with 10. We're dealing with 0.5 times 10 to the power 0. So that's why we have 0.5 as the error in theta. So the theta max shall be 30.5 and theta min shall be 29.5. So the maximum area shall be gotten from this formula. Now A max shall be, so we're going to be looking at the product of these values right here. So when dealing with the maximum, we're going to have A max times B max times sine theta max. And how do I know that? Is because when we're dealing with product, we just have max times max. Then now remember the maximum values. Remember here we're dealing with the maximum value of the theta itself. So that means it's this maximum value of the theta. So I have 30.5 inside the sine. So I'll have it this way, of which the answer shall be 4.465065 centimeters squared. The minimum value of error shall be gotten from this formula. So when we're dealing with products, everything shall become minimum. So this is what I'll have. So the answer shall be 4.041566 centimeters squared. Alright, so now to find the absolute error in area, I'll find it from this formula. So I have to know the maximum value of the area and the minimum value of the area, of which the answer shall be 0.21175. Now to find the relative error in area, I'll find it from this formula. Relative error shall be absolute error over the exact value. So I need to first know that exact value. So the exact value is got from here. So I'm going to put in the values as they were given. So it was 2.5 as the value of A, 3.4 as the value of B, and then sine 30. So I have 4.25 as the answer. So now I'm going to put that in. So I have 0.21175 divided by 4.25. So relative error shall be 0.049824. Now to find the percentage error in area, I'm going to have percentage error as relative error times 100%. So when I multiply the relative error times 100%, I'll have 4.9824%. And that is the answer they wanted. Alright, so the next question is a question from UNEB 2000. And this was question number 9. So I've been told that given that x is equal to 2.5, y is equal to 14.2, and z is equal to 8.1, all the values correct to one decimal place, find the maximum value of these. So we have x plus y over z squared, then we have x minus y over z, then we have 1 over x plus 1 over y minus 1 over z. So now because we've actually seen that the actual quotients here, we actually have to know what we're actually dealing with. So now here we have x plus y over z squared, and everything here is actually positive. So that actually means that here we're dealing with positive quotients. Now when I look here, I have x minus y at the numerator, which means I have x minus 14.2. I mean 2.5 minus 14.2, and that should definitely be a negative. So that means that in part 2, I actually have a negative numerator. So take note of that. Then these, we can actually just have the way they are. So all these correct decimal places. So I've been told to find the maximum values. Now part B, we've been told that if the errors in each of the values of ex and e minus x is that, find the maximum and minimum values of the quotient ex over e minus x when x is equal to 0.04, giving you answer correct to 3 decimal places. Now, first of all, we're going to first solve for those values at the beginning. Right, so now when I look at this value right here, I actually know that when actually I'm finding the maximum of quotients at the top, when they're positive, I have max at the top and minimum at the bottom. Now when I also look at addition here, addition, and I'm finding maximum, I have x max plus y max all over this z squared minimum. Now I can clearly see that x max is 2.5 plus 0.05, so I'm actually just saving time, so I actually just plug in the values as they are. Then I have 16.8 over 64.8025, and then the answer shall be 0.259 3 decimal places as they wanted. Now that is the answer for part 1. Now when I go to part 2, I'm dealing with x minus y over z, and I'm finding the maximum. Now remember, there we're actually dealing with a negative, so that means I'm actually looking at a maximum over a maximum, as you can see right here. So I'll have this. So because it's a quotient with a negative numerator, I'll have maximum over maximum. Then when I'm dealing with subtraction, the maximum shall be x max minus y min over this z max. So this is what I have when I plug in the values, and then the answer shall be negative 1.423 all to 3 decimal places. Now for part 3, alright, so in such an example we actually have to be very careful when we're actually dealing with them. So we're actually going to group this. So I'm going to group these together, then I'll have them subtracting what we actually have right here. So remember that when you actually group this together, so it should just be like this group minus this, and then we're finding the maximum. So in that case, I'll actually have it this way. So it will be like the maximum here minus the minimum right there. So basically, it will actually be the maximum here minus the minimum of 1 over z. But now when I actually look at the 1 over z value, now here we're actually dealing with a quotient. So what does that actually mean? So when I actually find the minimum of this 1 over z, the minimum of this 1 over z shall be gotten from this. That means I actually have a minimum at the top and the maximum at the bottom. So that's why I actually have a z max down. I can't put minimum here because this is actually a constant, and that's why I actually end up with that. So remember to be careful when you actually have ratios right here. Now when I actually look at this, now I'm also going to be adding these two, but now I should also consider the fact that I actually have a 1 over x and this is 1 over y. So when I actually find maximum in addition, it's basically max plus max in all cases. But now because this is actually 1 over x, I actually look at maximum in 1 over x. So maximum in positive quotients shall be a maximum over a minimum. So what that means is I'll have 1 over x min, and then here I'll also have 1 over y min in that case, all minus 1 over z max. So I hope you've actually understood what I've just done. So this is what I end up having, and then I'll have 0.356 or 3 decimal places. So for part B, we're being told that if the errors in each of the values, so we're looking at new values, ex and e power negative x is that. So we've been told the errors in each of them is given by that. Find the maximum and minimum values of the quotient ex over e minus x when x is 0.04, giving you answers to 3 decimal places. So for that case, we can first solve for ex. So now we've been told the errors in them, we know what that is. Then we've been told that x is 0.04. So when I actually press this in my calculator, I'll have 1.041 plus that, and the answer I'll get is 1.0415. Let's look at ex min. Ex min shall be this. So I'll have 1.0405. Now let's solve for e to the power negative x. This is what I end up having. So I have 0.961 plus 0.005, of which this is what I'll have, 0.9615. So when I look at the minimum value, I'll have it as 0.9605. Alright, so now that I know that, I can now first find the maximum value of ex over e to the power negative x. Now remember, when finding maximum and we're actually dealing with quotients, that now at the top I'll have a maximum over a minimum. So remember that when I'm actually finding maximum, I'll actually have a maximum over a minimum, and that is because both of the values at the top and the bottom are actually positive. So I have 1.0415 over 0.9605, which will give me 1.084 to 3 decimal places. Then the minimum value of ex over e to the power negative x shall be this. So when finding the minimum value of a positive quotient, it will be ex min over e power negative x max, of which I'll have 1.082, and those are the answers that they wanted. Alright, so lastly I have an exercise for you. These are questions you can actually try out to see if you've actually understood whatever I've been discussing in this first part of the errors video. So I encourage you to pause the video, copy these questions in your book, and actually just try them out. So this is question 1 all the way to question 4. The answers are actually given in brackets for you to actually make sure you're actually on the right track. And then the questions continue. So this is the next question, question 5. And then lastly, this is question number 6. So try this out and make sure you get better at the use of interval arithmetic. So in the next video, I shall be showing you how to use error propagation. So watch out for the next part. Thank you so much for watching today's video. I hope the video really helped you. If it did, feel free to share it with anyone that you can. And then if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit that notification bell so that you get updated every single time I upload a new video. Thank you so much for watching. See you in my next video.